You can't do cutting-edge research in any domain without relying on computing, connectivity, data. Those are areas where we're experts, and we feel like we have a very critical role for growing the entire research enterprise of Michigan Tech by growing these disciplines, and just as importantly, by reaching out and connecting to researchers in other spaces who rely on these technologies.
The Institute of Computing and Cybersystems, or the ICC as we call it, is an organization on campus that is surrounded around computing research. And so we're here, we exist outside of the conventional education that the university does within its departments, and we support faculty and student research.
The ICC is the perfect entity, the perfect unit to reflect the discipline-specific nature, because so many of the members of the ICC are from the College of Computing. Half of the members are from outside the college. That allows us to reach out, and I've yet to come up with a better analogy, as we reach out our tentacles and help others.
And the way that we do that is really through funding of research and personnel. So the ICC provides personnel that can provide help to faculty and students on writing grants, proposals, even papers, coming up with presentation material. And then we also have funds that are available to help students go to conferences and present their work.
We don't want to strangle them, we want to lift them up. And the ICC is perfect for doing that.
This is a Microsoft HoloLens AR headset. So it's a little different than sort of virtual reality. So if I put these on, I can still see. They're kind of like wearing like a big funny ski goggle or pair of eyeglasses. And so the HoloLens device, is an augmented reality headset that can project virtual content in front of you, and it can also detect, where your hands are. And so, besides interacting on surfaces, you can also just project a keyboard in midair. So I'm actually seeing. So there's a keyboard right here. So it's using cameras based on mounted on this headset to try and infer where all my fingers and joints and such are. While something like an AR headset can often sense, where your hands are, they're not accurate enough necessarily to detect, exactly when you tap. You can imagine if I had a table in front of me, we could have 4 different microphones attached to the bottom of that table.
Depending on where you tap, the 4 microphone will get it in a different time. And using that time difference, we can triangulate and locate where you tap.
And so that acoustic signal, we think, is going to be a nice way to detect the onset of interaction on the surface. Certainly an application of some of these ideas you could imagine in healthcare settings, especially, say sterile operating theaters, things like that, right? Like, so if you're operating midair, the nice thing is you're not touching any surface.
2 particular diseases we are particularly working on are brain aneurysms and aortic aneurysms. So for brain aneurysms, the problem is that it has a high prevalence in the general population. It's about 5 to 7% of general population over 18 has brain aneurysms. Problem is that if somebody has an aneurysm detected, it's not cause any troubles, and then it's not ruptured. Then what are you going to do with it? Because you put them conservatively, then you expose them with a risk of rupture, which is deadly. So we wanted to put all kind of information together to use the computer analytics, machine learning basically, try to predict. Some patients, they have aneurysm, but they are prone to rupture, so we need to treat them.
We get sent MRI data, so I'm going through and creating kind of a 3D model. This is kind of an ugly version of one of the 3D models that I'm doing. So I'm going to clean it up, make it look a lot more pretty, smooth it down.
We want to make a model to help the doctor, clinician, to see what will be the outcome of this aneurysm. It will be ruptured or unruptured. We calculate some new parameter which is related to the aneurysm, and then use this new combination in our classification.
So here will be the model here, the abdominal aneurysm. Here sees abnormal bulges here. And based on those parameters, we'll try to predict the status, fast growing or slow growing.
Abdominal aortic aneurysm, it's a big, serious healthcare issue. There's about 10 to 12% of senior over 65. In the United States alone, there's about 4 million people. So that's a very large patient base. So how to manage them, it will be interesting and challenging scenario. So we're providing those kind of information to the clinicians so that they can make better decisions. We call that precision medicine.
So we use a robotic device in my lab to assess motor behavior and cognitive function. It allows us to manipulate the dynamics of the environment in which people are moving, both mechanical dynamics as well as visual information on the screen. And then we can track the movements as people are making their reaching movements and generate kinematics about their behavior in order to quantify how they're performing the task and relate that to cognitive ability. We have 2 streams of research in my program. One is focused on just the basic mechanisms of how do those things change as we get older, and what is the interrelationship between cognitive and motor function. And the second stream is, if we can understand something about that relationship, can we use that information to design interventions that can hopefully improve functional independence in later adulthood, or can provide some diagnostic value in the clinic so that we can help identify individuals who are at higher risk of developing Alzheimer's disease. So we do a couple of different tasks. One is called a visual motor rotation. In those tasks, we ask people to move a cursor on a screen that represents the position of their hand. And then unbeknownst to the participant, we rotate the visual feedback about the position of their hand by 45 degrees, for example. And then participants have to, by trial and error, learn to aim 45 degrees in the opposite direction to get the cursor to go to the target or where they wanted it to go. And one of the other paradigms we use is called a force field adaptation experiment, where we apply a velocity-dependent force field where the robot actually physically pushes their hand perpendicular to their direction of motion, proportionate to the velocity of their movement. And then we measure how well they learn to counteract those forces over time by trial and error. The second part of our research is focused not just on the cognitive and motor function, but also on trying to quantify and understand the neural basis of those processes in both younger and older adults. So we use electroencephalography, and we measure brain activity concurrently while people are performing those cognitive and motor tasks. And our interest is in trying to understand what are the changes that happen in aging in the brain that lead to changes in these cognitive and motor functions.
I really enjoy that we can mix some of the motor learning with some neuroscience tests. I think that it's really some unique experiences that I'm getting here.
It's kind of nice to be part of the research that's hoping can kind of dive into, well, why does our body stop working quite as well, and what's that connection between the brain and the muscle control?
My research really have 2 broad areas. The first part is computing education and cybersecurity education. We have a CyberCop Scholarship for Services program. That is a scholarship for cybersecurity students. Basically, the US government provides full ride scholarship to 20 cybersecurity students. And the student, in turn, need to work for US federal government after graduation. That is one of the multi-million-dollar grant we got.
I was always trying to look towards the future, towards getting my master's degree, because I know that would sort of propel me into a better starting point in my career. And when I stumbled upon this scholarship opportunity, it was extremely attractive to me because I've always wanted to work in the government. So having the opportunity to get this scholarship and then knowing I'm gonna have a government job lined up really fulfills my future career goals.
We also do a lot of things with K-12 education. For example, like Gene Cyber Summer Camp. We have been working with over 300 K-12 teachers and students in the past few years.
So I've got a car that's a Raspberry Pi car that I know that Dr. Kai uses for his Gen Cyber camps during the summer. So it's got the same Raspberry Pi and then another chip with the OS on it. You can use it to teach basic programming either by drag and drop or Python, just depending on what your student's comfortable with.
Drone security is also a critical issue because drone was controlled by the wireless signal through the base station, and that can also be intersected or hacked by hackers. Especially in the
military usage. What we do is we set up a drone test bed, which has multiple drone fleet, and those drones communicate with each other, and those drones are controlled using a mini computer Raspberry Pi. And then the communication between those drones need to be secure. There's all type of possible attacks on the drones, which we can simulate using the drone platform. And based on that, we can study what are the most effective mechanisms to secure the drone and defend against all different type of attacks.
So I've been working with Chuck Wallace for many years on a community computer support group for community members. One of our wild and crazy ideas was, well, what if we could just teleport right into the middle of their living room? And so we're developing a piece of technology, a portal, if you will, that people will be able to instantly connect with a live human tutor and take advantage of our basic tutoring program, which stands for Building Adult Skills in Computing. We have to design the software, the interface, as something that a person who doesn't know how to use computers at all could pick up and instantly access it. We have several researchers in our department that are looking at various aspects of driving, using the driving simulator to better understand human cognition, human interaction with systems. The participants were sitting in the driver's seat, either asked to keep their hands on the wheel or the eyes on the road, and about halfway into the drive, we flipped the outside world, right as they're driving under an underpass. The person is effectively driving on the wrong side of the road signs are backwards. It's the kind of thing that most people think, this would be weird, I would totally notice this. But indeed, over half of our participants did not. And this remained this way for about 15 seconds. But we did find some differences in things like mind wandering. And so our future work, we're going to move it into the driving simulator so we can look more at what happens after the takeover, like what happens when a person re-engages, looking at performance and the different aspects of these driver engagement strategies.
My research is on how people make sense of ambiguous situations and question their theories about those situations, and then rated on a number of factors which we used to sort of determine how people were thinking about the situation and the theories they were generating and how they questioned those theories potentially.
So this research is using rule-based learning to train an AI or machine learning system. The algorithms of the system are unknown, so how do you teach such a complex system? So what we've done is we've gone and we've discovered that using a rule card where the rule is stated for training, and then there's a visual depiction of it, and then there's the base rate of it, and another description of it, and using this rule card to train individuals, they had higher scores in predicting the output of the AI or machine learning system.
My research is on how to incorporate cognitive empathetic elements into AI systems for especially healthcare systems. So normally when we think about empathy, it is very important for patient-physician relationship, and if we want to use AI systems to interact with patients, so we need them to be empathetic as well, but they cannot be emotionally empathetic in reality. So we are thinking how we could incorporate cognitive empathetic elements, just like how if they could show that they can understand human reasoning, their situation, their perspectives, so that would be maybe more satisfactory and trustworthy for patients.
In this research, we are looking into drivers' behavior in presence of a warning system in a rail crossing area. So the warning system comes from a connected environment, like a rail signal box, and the car communicates with that signal box when there is a train present to that, and the driver knows and can stop in time when there is a train in the track.
So this kind of goes into like the video game research that our lab does. We kind of look at two different facets of how like video games can play into people's lives. So particularly we look at creativity and problem solving, especially like problems that have to do with like insight. So we found that especially with the creativity that people who are non-gamers who play video games don't actually have an increase in their creativity overall. So it's not so much an excess and quantity of their thoughts, but the quality of their thoughts are better, so more original thoughts.